This is actually an old step 1 question from 2000, question number 10, but it's now in the step 2 curriculum. So it's question 6 from the step 2 mechanics support module. So you have three particles, P1, P2, and P3, masses M1, M2, M3. P1 is projected towards P2 and brought to rest by the collision. P2 then is obviously moved to the right and collides with particle 3, and the latter moves forward with speed v. So I've condensed this all down to this. So P1, the particle 1, hits particle 2, which has speed 0, and it is brought to rest by the collision. So it was traveling at v, now is at 0. This one was at 0, now it's traveling, I've just called it v1 after it gets hit. And then in the second collision, it's traveling with speed v1, hits M3, which is stationary, and now travels, let's just say, at v2, whilst the third particle travels at v. So I think I've got all of that sorted. And now we just set up conservation of momentum and the coefficients of restitution equations for both of the two collisions. So here, of course, the zeros help you out a lot. So the conservation of momentum is super easy. And the E is also super easy. It's just going to be this one over this one. And over here, the same sort of thing, slightly more complicated. And then the E is this one minus this one over this one minus this one, which is going to be this here. So that's all good. And now all we really need to do, such as the case in mechanics questions, is ignore our picture now that we've set it all out and got these four equations, and just try and use these four equations to try and get here. So, okay, I've already got an E dashed equals, it's right there. So my plan here is just to rewrite all of these in terms of V, V1, and V2, and then just throw them in here and hope that everything cancels. So starting with this one over here, V1 is this business. And then I guess we can say over here that V1 is also this. Now, kind of interesting is that, of course, if V1 equals both those things, then these two things equal each other, and then we can cancel the V's and we get E as this. That might be helpful later. But for now, yeah, my plan is to write the V1 and V2 in terms of V, because now the same thing is going to happen if I do that. Like if the V2 has been written in terms of V and the V1 in terms of V, then all the V's would just cancel, and I'd just be hopefully left with M's, just like I did here, but kind of in a larger scenario rather than just these quick lines. So okay, I've got V1 in terms of V, so that's ready to go. Now I just need V2 in terms of V. So let's rearrange this for V2. I get this, and now this has a V1 in it, which I don't want. So let's just throw this V1 into there to end up with this. And now I think my plan is fully enacted, because V1 I can replace with this stuff. V2 I can replace with this stuff. And then because every single term will have a V in it, I think I can just cancel all the V's out, and everything will be fine. The only issue is this E here, which it doesn't have over here. But E I've already written in terms of M, so that's fantastic. So that's also going to help me out massively, because that's just, and this E as well, I guess, because that's just M1 over M2. So I can replace those guys in there as well. So that's just me cancelling all the V's. And now this is me writing the E's as M1 over M2. Of course, M1 over M2 here just cancels the M2s out to leave an M1 behind, or there, I should say. And yeah, now this is M2 over M2, which takes away from this. And then these M2s can cancel, open up brackets, and we end up precisely with what they wanted us to get, which is excellent and wasn't too tricky to get to. So that's fantastic. Back to where we were then. So show these things for these collisions to be possible. So what do we know about E dash? Well, we know it must be between 0 and 1 because it's a coefficient of restitution. So let's just say that this thing here has to be less than or equal to 1, therefore, which means, of course, that because M1 is a positive number, we can just times it across. Or we can just say, well, this is a fraction less than 1, so the numerator's got to be less or equal to the denominator, I guess, is another way of just looking at it. Add M1 to both sides, and we end up with this, which is this condition over here. And then the other one, of course, E dash greater than 0, so that just means the numerator has to be bigger than 0. And move the thing over, and you get this here, which is the two conditions precisely I wanted us to get. Now it says if M1, M3, and V are fixed, find in terms of those things the largest and smallest values for the kinetic energy. Or it just says the final energy, but the only energy here is kinetic, right? So, okay, well, what's the final kinetic energy here? Well, that one stops, so it's completely irrelevant, which is kind of weird because this is the one that has M1 in it, and I'm supposed to get this in terms of M1, but okay. So the only kinetic energy at the end here is a half M3V squared and a half M2 V2 squared, right? This speed is just the one that was carried over to this final thing here. So this is the final kinetic energy. Now, it doesn't want any V2s, so we're going to have to get rid of those. And the way that we're going to do it is the same thing I did before, right? I'm going to use this equation, which is the one that connects V2 to V and V1, and I'm just going to rearrange it for V2. In fact, I'm going to rearrange it for M2 V2, because there's an M2 sitting right here, except this is M2 V2 and the V2 is the 1 squared. So what if I just times this one by M2 over M2 and made it look a bit more like this? Because then this M2 V2 is all being squared. So I could just replace it with the square of this, and that would give me V's, 1s, and V's, which is better. It's not amazing because obviously they don't want V1s either, because V1 and V2 are the two things I invented, right? So that's why they don't want those things. But of course, in order to get rid of this V2, I can only really turn it into a V1, and then hopefully using the coefficient of momentum, the conservation of momentum of this one, I can turn that V1 into a V. So I can replace this V1 with M1V over M2, which will cancel this M2 here, which is nice, and we'll just be left with this here. So this, I think, is in terms of M1, V, M3, and that's it. Oh, sorry, there is also an M2. Sorry, there is an M2 there. So, okay, so I've got almost everything. It's just this M2 is not so good. There's no obvious way of getting rid of that. In fact, there's no way of getting rid of it that doesn't introduce other M's that I don't want. And that's where this largest and smallest possible value of it comes in. Like the idea is, I just factorized out some stuff. The idea is that it doesn't really want me to get rid of this properly. It wants me to get rid of it in a way that then describes the largest and smallest possible terms. This is why they made us do this. Although this itself isn't that helpful. What you're thinking here is, well, if I want to maximize this, that will mean minimizing M2. Because like all of this is just positive numbers, right? So if I divide by something as small as possible, this becomes as big as possible, and then the whole thing becomes as big as possible. So that's when it's max, and it's minimum in the reverse, right? When M2 is as big as possible, which is great because here, this is why they prepped you for some inequalities. But they don't describe M2. So let's make them describe M2. So let's take away M3 from both, and we get this. And so on the face of it, all I have to do is say, well, the smallest M2 can actually be is this guy here. So let's just throw that guy into there and say that means that the maximum kinetic energy is just this. And likewise, the minimum is when M2 is as big as it can possibly be, which is this here. And actually, this would lose you a mark or two. I'm not really sure. I haven't looked at the proper mark scheme. But there's a really nice little, or I say nice, there's a very cheap trick thrown into here, which means that this will lose you a mark or two. And it's from way earlier when we saw this. Like, sure, these conditions have been written out because of E dash being between 1 and 0, but there was another E going on here, and that also had to be between 1 and 0, and therefore M1 has to be less than or equal to M2, which actually gives you a stricter bound for M2 than this does, right? Because this is smaller than M1 because the M's are all positive. So actually this bound it's correct, but it's not strict enough. It should be M2 strictly bigger equal to M1 more specifically, which means you then the smallest M2 can actually be is M1, not M1 take away M3. And so you just throw M1 into here instead, and you say that's the maximum it can be, and that's the minimum. The minimum is actually correct. There's no better bound for that. So yeah, therefore, that will be our answers. Thanks for watching. I'll see you next time.